Welcome back now to the 53rd lecture of the course, and which we started to discuss energy balance with chemical reactions. And in the previous lecture we have learnt a very important law, which is essentially the Hess law, and we have seen how Hess law can be used to circumvent the problem of compounds or circumvent the problem associated with calculation of the heat of formation of compounds which have a fake formation reaction, which we have already noticed. What we plan to do now, we will take up in the next couple of lectures. We will continue with Hess law, or rather it will be primarily based on application of Hess law, where we will show, or I will teach you how one can calculate the heat of formation not only from heat of formation of other compounds which have real formation reaction, but even other type of reactions whose heat of reaction values can be easily measured. And one such type of reaction is of course the combustion reaction, right. So, we have this so called concept of standard heat of combustion typically it is represented by Hc0, right. So, this is essentially nothing but the heat of reaction of a substance resulting from oxidation with molecular oxygen. So, this is heat of reaction of a substance that results from oxidation of it, or not from results, due to oxidation of it with molecular oxygen. And this class, now I know that in the other part you have had detailed discussion on combustion reactions, etc., etc. So, here what we essentially do, we have a combustible compound, and what you essentially look at is the heat of reaction associated if you burn it or combust it or oxidize it in stoichiometric oxygen only. You do not consider any excess air, or you do not consider nitrogen is present or whatever. It is sort of, so when you are calculating the heat of combustion, please do understand that you are not talking about the air that you are pushing into the reactor or the combustion chamber, because the oxidation reaction only takes place with molecular oxygen and in stoichiometric amount, and this can be measured, right. This can be measured. So, typically most organic compounds are combustible, and therefore, the thermochemical data for many organic compounds are reported or easily available in the form of heat of combustion. Typically, thermochemical data for many organic compounds are available data of heat of combustion. Let me use the symbol now, sorry for this little bit of mix up. For many organic compounds are available, right. However, for many of them the direct heat of formation data is not available, and very interestingly, even the data may combustion data in certain cases, this is just for your knowledge, but this is a very interesting one. Combustion data in certain cases are also available for many substances that are not combustible under regular condition. This is interesting. So, example of which include CCl4, chloroform and stuff like that, right. These are available. Of course, when we are talking about the standard heat of combustion, it now should immediately come to the mind of this class that we are essentially talking about this combustion reaction. What is the condition? Combustion reaction taking place at 25 degrees centigrade and 1 atmospheric pressure. So, the reactants enter and products leave at 25 degrees centigrade and 1 atmospheric pressure. So, typically what you need to understand that since all the combustion reactions are exothermic, so heat gets generated and therefore, the flue gas that eventually comes out of the combustion chamber is typically hot. Even if you hold your hand in the exhaust, in front of the exhaust of your car or bike or whatever, right, you will see that a hot gas is coming out. So, that is nothing but flue gas. So, whatever you have studied as flue gas, one of the classic example is that the vent, that is the exhaust that is coming out from an automobile engine, is actually flue gas. And many times you might have noticed, particularly for our students who are joining from the northern part of the country, you might have seen that in winter months, some water drips out of this exhaust chamber, right. You might have noticed this, and even if you have not noticed, coming winter please notice it. So, now this class should immediately understand what it is, and what it is nothing but the H2O, the water present in the exhaust, has, because of low temperature outside, has condensed into water, and under what condition this condensation takes place we will learn when we talk about humidity, right. So, of course, so the take home message is that of course, what you have is a combustion reaction, right. So, energy gets generated, some part of energy is used in sort of driving a motor or moving a shaft or whatever. So, that is essentially an internal conversion of energy from one form to the other, but more importantly the products are coming out at a higher temperature, right. So, here if you are willing to measure the standard heat of combustion, you need to ensure that the products are also coming out at 1 atmospheric pressure and 25 degrees centigrade. So, essentially you have to cool down the product, and therefore, based on that the total heat that gets generated by the system can be measured, and that is essentially the heat of combustion. Okay. So, this is easy stuff. Now, what I will do, as I already promised in the initial introductory part of this lecture, that I am going to pick up an example of an unique system where, let us say for chloroform, I am going to show the heat of combustion data is available, right, but the heat of formation data is difficult to obtain. So, it is like that. So, essentially the problem we are talking about is application of Hess law, and it is calculation of heat of formation from heat of combustion. So, what is the problem? Let us pick up. The problem is the combustion reaction, what is given, the heat of combustion for chloroform is given. this is given, okay, and you are told to find out this. Now, what I am going to do is I am going to show this problem, how to tackle this problem stepwise very slowly, so that you understand and you all pick up how we are applying Hess law, and then subsequently you can solve this for other type of compounds, which I will try to give some examples in your assignments. Okay. So, in order to solve this problem, we essentially need to know certain things which are all given. I am coming to it, but let us try to first figure out what are the stuff we need to know, right. So, we must have an idea. So, the stuff we need to know is, number one, we need to know the combustion reaction of chloroform, right, which is not a very straightforward reaction, right, because have you ever heard that chloroform is being used as a fuel? The answer is no. So, the combustion reaction of chloroform, let me write it down for you, and this is at the learning stage. So, it is perfectly fine. So, it is something like this. They call it aqueous, it is actually liquid, equal to CO2 plus 3HCl. See, I have already made a mistake as I am writing a reaction, I should write it CO2G, right. So, this is the combustion reaction. So, essentially when you are told that the heat of combustion of chloroform is actually given, so what exactly is given to you? What actually is given to you is the heat of reaction, right, of this particular reaction, that is what is given, okay. And what it is? So, when you say that heat of combustion of chloroform is given, that means actually what you have is the heat of reaction for the above reaction, and this turns out to be, what is the heat of combustion in this particular case? It is going to be heat of formation of carbon dioxide plus thrice the heat of formation of hydrochloric acid minus heat of formation of water minus heat of formation of CHCl3. So, this is what you need to find out. This is the stuff that you need to find out, right. And of course, in order to progress, we now understand that we need to have the heat of formation data of carbon dioxide, heat of formation data of HCl, and heat of formation data of water, right. So, this we will need, but more importantly, let us see what we also know. So, I am going to show it in terms of Hess law, right. So, what we also know or need to know, the formation reaction of chloroform, right. So, the formation reaction of chloroform is as follows. Okay. So, this is how it goes. Okay. Now, let us try to apply Hess law. So, this problem if you can directly, since you know the heat of combustion data here, so you can straight away do a substitution. So, from this equation you can write that heat of formation is equal to heat of formation of chloroform is equal to heat of formation of carbon dioxide plus thrice heat of formation of HCl minus heat of formation of water minus the heat of combustion of chloroform. So, you can straight away calculate that, but I am going to show you how you get that in terms of through Hess law. So, let us see how we get it. So, this is the formation reaction of chloroform, this is something we also have, and let us also look into the formation reactions of these three compounds: water, hydrochloric acid and carbon dioxide, right. So, the whole purpose of this problem is essentially to showcase to you the application of Hess law. It may not be useful in this particular case, but there are situations where you might have to solve stuff like this. Right. So, let us mark this as equation 2, this as equation 3 and this as equation 4, and let us mark this as equation 1. So, what are we trying to get? We are essentially trying to get an expression for the heat of formation of chloroform through the heat of combustion data that is available to us. And for that, let us see what we are going to write. We are essentially going to sort of using Hess law. So, we know that we can add on or subtract equations. So, let me just copy part of this equations in the next slide, that will make it easier for us to follow, right. And so, let us get rid of this one and so what we have are these equations. Okay. So, now what we see is I am going to show you how you get an idea about the applicability of Hess law. So, you see that for this combustion reaction, what we have is on the right hand side, we essentially have CO2 and 3HCl. So, let us get started with getting something that on the right hand side will give us CO2 plus 3HCl. I have already told that this problem you can go to the previous stage, straight away plug in the numbers here and can get a solution. But what I am going to, what the reason I am taking this longish route is to demonstrate where Hess law comes into picture. So, what we first do, we try to match this right hand sides. So, we do that you can get if you write, and for Hess law you essentially treat the chemical reactions as sort of algebraic equations. So, if you do this equation 3 plus 3 times equation 4, so you see that 3C plus 3O2, I am just not writing the states because this is an intermediate stage, plus 3 by 2 H2 plus 3 by 2 Cl2 is equal to CO2 plus 3 HCl. Okay? This is what it is. Now, finally, we need to have an expression for heat of formation of chloroform. Therefore, we should bring in the heat of formation of chloroform here. So, how can we bring that in? We can bring that in by introducing or let us say subtracting, right, the heat of formation. So, now the logic is as follows. So, now we have this composite equation 3 plus 3 times equation 4 is giving CO2 plus 3 HCl, and you see over here that the right hand side is CO2 plus 3 HCl. So, the best thing to do about is now to subtract equation 1 from this. So, this will give us 3C plus 3O2 plus 3 by 2 H2 plus 3 by 2 Cl2 minus CHCl3 minus half O2 minus H2O, and on the right hand side you essentially get 0 because you have CO2 plus. So, let me write it down, CO2 plus 3HCl minus CO2 minus 3HCl. So, you get 0. So, now you see what are you trying to get? You are trying to recombine these equations, these 3 heat of formation, the 3 formation reactions and 1 combustion reaction over here, right, to get essentially the formation reaction of chloroform. That is what you are trying to do. So, you now see that you already have chloroform. So, definitely chloroform is going to be on the right hand side, right, but what you also observe is in this composite equation you actually have water sitting over there. So, you need to eliminate this water because water is not there in your formation reaction of chloroform, right. So, here you see you have carbon, hydrogen, chlorine. So, here you see you have carbon, here you have hydrogen, here you have chlorine, and right side is 0 because all this gets cancelled out. So, you can transpose the chloroform to the right hand side, right, and you can essentially get certain stuff in terms of chloroform, but the spoil sport is you still have water sitting over here. So, what we now do, so how can we eliminate water? We can eliminate water if we do something, right, if we do something to with the or add or subtract to this composite equation now, and this is what is the composite equation in its present form now. If we simply subtract the formation reaction of water from this, from the both sides. So, finally, what we do? We essentially do we subtract the formation reaction of water, and that leads to 3C plus 3O2 plus 3 by 2 H2 plus 3 by 2 Cl2 minus CHCl3 minus half O2 minus H2O minus H2 minus half O2, and what you get on the right hand side is minus H2O, because here you have 0, the RHS at this stage is 0, and from that you are subtracting equation 2, right, you are subtracting equation 2. So, right hand side is minus H2, right. So, this I could have done in one single step, but I just wanted to show you how logically you proceed with this combination of equations, right, so that you can, applying Hess law, get to the formation reaction. That is the only logic. I repeat again, please do not get confused. So, we could have simply used this expression over here, right, to get the heat of formation, but what I am trying to show that by manipulation. So, one thing is to get the heat of formation value, and that is fine, most of the time you know that is what you need, but what you are I am showing here is a direct application of Hess law, how where you can essentially get not only the value, but you also learn how to get the heat of the formation reaction, right, using the heat of combustion reaction of that particular compound along with certain other, so byproducts or other reactants or whatever you have, their formation reaction. So, I hope you are all of you are clear as to why we are doing this laborious exercise, because finally as far as the numerical part is concerned, we will actually get these values, and you could have simply plugged in those numbers and obtained the final value, right. But the whole purpose of this lecture is to demonstrate the applicability of Hess law in a broader perspective. Okay. So, now if we decide to look into the terms on the left hand side and right hand side. So, first thing we observe is this, there is a minus H2 on the left hand side and a minus H2 on the right hand side. So, that gets cancelled out, and your whole purpose of eliminating this H2O, which was sitting in the intermediate composite equation, is achieved. Now, let us look into the other stuff. So, we have a minus chloroform over here, which we can transpose to the right hand side, and let us see what are the other stuff we have. I must have made a mistake somewhere, right. Equation 3, see I made a mistake here, there is no reason. Equation 3 is C plus O2 equal to CO2. So, these 3's will not be there, this was a mistake on my part. So, yeah. So, now you see that you have oxygen, right, and 1 oxygen plus, here you have half oxygen minus, here you have half oxygen minus. It might seem very simple to many of you, but I would prefer to go it step by step like this, so that everybody who has joined this class and sitting with a pen and paper can understand what exactly is going in, rather than jumping steps and teaching maybe 10% or impressing 10% of the students, right. So, that is the whole logic. So, this you are done with, and now you see, so you have a carbon, you have 3/2 chlorine, you see you have carbon over here, you have 3/2 chlorine over here, but you also have plus 3/2 hydrogen, which you actually need half hydrogen, but you see over here plus 3/2 hydrogen minus hydrogen. So, this 2 combines essentially, and what you eventually have is half hydrogen only, right. So, I do not want to change slide. So, if you kindly allow, I will write over here. So, what we finally get is C plus half H2, of course, you have to write solid and gas and everything at every step, right, plus 3/2 Cl2, which is aqueous, minus CHCl3 is equal to 0. And as I have repeatedly told, in the context of Hess law, you actually treat the chemical reactions just the way that they are as if algebraic equations. So, you are very much allowed in this context to write right. Sorry, it is not aqueous, this is gas, chloroform is gas, right. So, now what is the take home message? We are reaching the end of this class, but what is the take home message? Take home message is that combining, or this is the way to essentially by which I have shown how you can get the formation reaction from combustion reaction. And what are the operations you have done? You have done equation 3 plus thrice equation 4, sorry, I should look into here. You have done equation 3 plus thrice into equation 4 minus equation 1 minus equation 2. So, all you need to do is you simply add up heat of formation of water plus heat of formation of carbon dioxide plus thrice the heat of formation of hydrochloric acid minus the heat of combustion of chloroform minus heat of formation of water, and you see that is exactly the expression you have over here. So, where you can simply plug in these numbers and you can just do it yourself. If you plug in these numbers appropriately, the heat of formation or the heat of reaction value will be minus 94.051, sorry, I probably did not write the values, 40.023 minus of minus 121.80 minus of minus 68.317, and that will give you minus 24.003 kilocalorie per gram mole. I just made a mistake. So, the heat of formation values for water, heat of formation value of water is minus 68.317 kilocalorie per gram mole. That for carbon dioxide is minus 94.051, and that for hydrochloric acid is minus 40.023. So, if you know these numbers, you can straight away calculate, but what I have demonstrated how you can take advantage of Hess law in generating, reconstructing the formation reaction. So, I would request all of you to kindly practice this and with other compounds to get a better feel of applicability of Hess law. Thank you.